Welcome to the session 8 of module 4. In this session, we are studying about construction of state diagrams. These are the contents that we are studying in this session. We are taking two examples, up-down decade counter and sequence detectors, in order to write a state diagram for that. Construction of state diagrams. State diagrams are nothing but a graphical rendition of a sequential circuit. The development of state diagrams from the verbal statement or problem statement is the most challenging part of sequential circuit synthesis. In order to get a state diagram from the verbal statement, the translation of a problem statement into a state diagram requires several attempts before the final state diagram is reached. And the construction of the state diagram in sequential design is analogous to the construction of truth table in combinational logic design. In the first module, we studied about how to write a truth table for the combinational logic design. If they give the problem statement, when they give the problem statement, we have to check the inputs and output of a function, and then we have to find out the last equation, the final equation for that problem. In the same way, the construction of the state diagram requires many attempts before we get a final state diagram. First example, up-down decade counter. What is decade counter? The counter which counts from 0 to 9. Here the problem is create the state diagram for a synchronous decade counter. The counter is to count up or down in binary depending on the value of a mode control input signal. It has to count up and down in binary. We know the equivalent binary values for the numbers, decimal numbers 0 to 9. Depending on the value of a mode control input, that is if m is equal to 0, the counter is to count up. If m is equal to 1, the counter is to count down. We have to write a state diagram in this way. The counter is to repeat our cycle. That is to count from 0 to 9 and then start over if m is equal to 0, or count down from 9 to 0 if m is equal to 1. The counter output y is to be a 1 if counting up and the terminal count is reached. If it counts from 0 to 9, for the last state, the value of y should be 1. If it completes one cycle of counting up, y should be 1. And another output z is to be a 1 at the terminal count if counting down. Should the mode control value change during the count sequence, outputs y and z will be asserted when the terminal count is reached. When the terminal count is reached, this y and z values will be asserted. That is, it will be high. From the description of the problem, how many states we require? We require 10 states. We require 10 states because decade is nothing but 10. It is nothing but 10. So we require how many states? 10 states. Single mode control determines the count direction. Here we are considering the mode as m. If m is equal to 0, it will count up. If m is equal to 1, it will count down. Because the problem stated that the counter must be synchronous, the circuit is to count an input external event when it is coincident with a clock. Okay, since it is we are constructing a synchronous counter, the circuit is to count an input external event when it is coincident with a clock. The state diagram is developed as follows. Okay. Draw 10 state symbols and label them from 0 through 9. Total 10 states will be there. Second step, determine the mode control value. Let m be 0 for count up and 1 for countdown. And while writing the state diagram, the states will be represented inside a circle, and the directed arcs represent the transition of data from one state to the other. Okay, one state to the other. Connect each state symbol with a directed arc. Connect each state symbol with a directed arcs, indicating the next state for the two values of m. Here for m is equal to 0, it has to count up. It has to count up. When m is equal to 1, it has to count down. So, first step is to write 10 states, 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, here we are representing it as in decimal. Okay, but we can also write it in the binary value, no issues. And here we are transiting from one zero state to one state when we are having mode control as 0. Here instead of m is equal to 0, we are writing it as m bar, which represents that m is equal to 0. And from state 1 to 2, it is counting up. It is transiting from state 1 to 2 when it is m bar. In the same way, it is transiting from 0 through 9, 0 through 9 for count up. Okay, for count up, it will transit from 0 to 9 when m is equal to 0. Okay, when m is equal to 0. Now to represent m is equal to 0, they are representing it as m bar. For countdown, we are considering m value as 1. Okay, mode control as 1. See here, for countdown, we are counting from 9 through 0. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Again, it is repeating. Okay, when it completes the whole cycle, then we are asserting y and z. Okay, you can see here, after the completion of count up from 0 to 9, we are asserting y, m bar slash y, which means that m is the mode control and y is the output. Okay, where after the completion of one cycle, we are making it as y as high. Okay, and then after the countdown, after it finishes counting from 9 to 0, we are asserting z. Okay, for count up, mode control will be 0. For countdown, mode control will be 1. That is m. Okay, after the completion of one cycle, okay, we are asserting y for count up and we are asserting z for countdown. Okay. Connect each state symbol with directed arcs indicating the next state for the two values of m. Here for the count up and countdown, we are representing in the same state diagram. Okay, this is the writing the state diagram for the up, down, decade counter. Okay, decade is nothing but 10. Okay, 10. And here we are decade starts from 0 to 9. 10 states, total 10 states. Okay, we are representing states which are encircled with the symbols, and then the directed arcs represents the transition of state from one state to the other state. Okay, to count up, we are considering mode as 0. For countdown, we are considering mode as 1. And after the completion of cycle, we are asserting y for the count up, we are asserting z for the countdown. The state diagram is a Mealy mission because the two output variables are dependent on both the mode input and the present state. Okay, here the mode input and the present state. It has to check for the state whether it has completed whole 10 states or not. Okay, if it is not completed, it will not, we are not getting the output y. So it is a Mealy mission. It depends on both the input mode control and also the present state. So it is a Mealy mission. example, sequence detectors. We will be having a particular sequence of input string, and we will be having a sequence that we have to detect in that given sequence. Okay, and we will see this example. Construct a Mealy state diagram. Construct a Mealy state diagram that will detect a serial input sequence of 10110. The detection of the required bit pattern can occur in a longer data string, and the correct pattern can overlap with another pattern. Okay. When the input pattern has been detected, cause and output Z to be asserted high. Here we are having the sequence X. This is the input sequence, and this is the output that we get. Okay. Here we have to check for the string, check for the sequence 10110. Okay, 10110. And the detection of the required bit pattern can occur in a longer data string, and the correct pattern can overlap with another pattern. You see here, X is equal to 10110. We are getting 10110 at the starting of the string only. And then after this 101, again, here, these two bits are overlapping. Okay, that is, again, we are getting another pattern, another sequence, that is 10110. Okay, the correct pattern can overlap with another pattern. Okay, in the same way, here the starting bits for the sequence that we have to detect is 10. Again, 10 is overlapped with the previous sequence, that is 10110. So when we get the output, the sequence 10110, okay, serial input sequence of 10110, after the detection of a sequence, Z will be high. Okay, first we'll check the input 1, next 0, next state 1, 1, 0. After we get all the 5 bits of the sequence, we are asserting high, which means that we have detected the sequence. Z represents the output. After the detection of the sequence, we are asserting the Z. Next, here 10110. Here it is overlapped with the previous sequence. So we can also consider that 10 along with the other 3 bits. Here 10110. So we got the sequence again. So we are asserting Z. Again this 10 is there. 10110. Again we are asserting 1. After the 5 bits are detected, we are asserting a Z. The bits may overlap with the previous one. Okay. Now we have to construct a state diagram for this. The input pattern requires a single input variable X. A single output variable is used to indicate detection of a correct input pattern. If an incorrect pattern is presented, no output occurs. If we get a correct input pattern, then only we are asserting Z. We are asserting Z. Okay. Otherwise, we are representing Z as 0. Okay. First step, develop the state diagram one state at a time. The LSB to be detected is a 1. State A is the initial state. It checks for 1. If a 1 occurs, the machine changes from state A to state B. What is the sequence that we have to detect? 10110. First, it will check for 1. Okay. Let us consider we are having initial state as A. We are checking for this input 1. Okay. Now, if we are getting the state or input bit as 1, then we are going for the next state B. What is the output? Output is 0. If we are getting the first bit as 0, okay, we will be in the same initial state. We are not going to the next state. Okay, if we are getting the proper input sequence, then only we are going to the next state. Otherwise we'll be in the same state or current state. If your first bit is 0, we will be in the same state. We are not transiting to the next state. When the input bit is 0, Z will be 0 because we are not getting a proper output sequence. So we'll be in the same state and the output is 0. Okay. If a 0 occurs, the machine remains in state A, waiting for the first one. Yes. See here, we will be in the state A, that is the initial state or starting state. When we are having the first bit as 0, okay, in this first bit as 0, then we will be in the same state. We are not transiting to the next state because our required sequence is 10110. We have to detect the sequence. Okay, if you are detecting the bit 1, we are going from the starting state to the next state to detect another bit. Okay, your first initial state will be A. If I am getting the first bit as 0, then I will be in the same state. I'm not transiting to the other state. If I am getting 1, I am transiting to the other state. Now, second step. The correct second bit in the string is a 0. Now, what is our string? It is 10110. Okay, it is 10110. Now, in the first step, we got the correct bit as 1. So we are transiting to the state B. Okay. Now we have to check for the second bit 0. If we are getting the second bit as 0, then we are transiting to the next state. Otherwise, we'll be in the same state. If our next bit is 1, we are not transiting to the next state. We'll be in the same state B. Okay. What is the input? 1. Output is 0. Which means that we are initial ones. Okay. Again, we are starting from this state B because the first bit is 1 here. Okay, and after that, if you are getting second bit as 0, then we are transiting to the next state C. Okay, if a second one is detected, it is to be counted as the first correct bit in the string. Okay, you see here we are getting the first correct bit, that is initial one, output is 0. Okay, we are transiting to state B. If you are in state B, if you are getting the next bit as 1, then which means that we are in the initial 1 only. Okay, initial 1 only. And if you are getting 0, we are transiting to the next state. Okay, state B represents the fact that a 1 has been detected. If multiple 1s occur, the last one is counted as the first correct bit in the desired input string. The state transition for initial 1 and second 0. Here, if you are getting again bit as 1, it will be in the state B, and we are considering that state as the starting state. Okay, that bit as the initial bit. Okay, this bit, and then this is second bit 0, and the output will be 0. Okay, here next what we have to consider is the next state. Okay, here we have to detect the sequence 10110. We got 2 bits 10. Next we have to check for the next bit 1. The third correct bit in the input string is a 1. A transition from C to D occurs if a string 101 has been detected. Okay, if an input string is 100, the machine goes back to state A because 100 string cannot be a part of the correct input string. Here we are initial state will be A, and next we are transiting to state B. Okay, when we the first bit is correct here, the first bit is correct here, and our sequence is 10110. Here the first bit is correct. Next we are transiting to state B. Then at state B, we are checking for the bit. If it is 0, we are transiting to state C. If it is 1, will be in the state B. Then we are considering this bit as the starting bit for the sequence that we have to detect. And here, when we are in state C, we have detected 2 bits, that is 1, 0. Next, at state C, if you are getting 0, again we are going to the state A, because 3 bits, that is 1, 0, 1, we are not detecting 1, 0, 1 here. The third bit is wrong. So we are going to the initial state. Again, we are checking the sequence from the initial state. Okay. Next, when we get 1, we are going to the next state D. Okay. When we are getting 1, which means that we have detected 3 bits, 1, 0, 1. Okay. And then we are going to the state D. Okay. To check the sequence, whether it is detected or not. Now, if the third bit is incorrect, we are going to the state A. Okay. Because again, we have to start the sequence from the first. The fourth correct input bit in the serial string is checked by the transition from state D to either state E or back to state C. Okay. Here, first bit is detected here. Here, second bit is detected, 1, 0. 1, 0, 1, 1, 0. First bit is detected, second bit is detected, and third bit is detected, 1, 0, 1. Now, if you are in the state D, okay, here if you are considering this C state as the starting sequence, that is 1, 0, again, see here, your state is C here, and then you are transiting to D whenever the input is 1 and output will be 0. This will be the starting of the sequence, okay, because our sequence is 1, 0, 1, 1, 0. Okay, here we are considering C to D as the transition, given the input is 1 and the output is 0. And when it is in state D, when the input is 0, it goes to state C again. Okay, because here our sequence is 1, 0. Again, we can transit from C to D, and then D to E, and then E to C to complete the sequence. And after the detection of the sequence, we are asserting Z is equal to 1. Okay, here, when it is in state A, we are checking for the input bit, whether it is 0 or 1. When it is 0, it will be in the same state. When it is 1, we are going to the state B. When we are in B, current state B, if we are having input bit as 1, then the sequence will be incorrect. Okay, so whenever we are getting the next bit as 0, it is correct. Okay, 1, 0. If the next bit is 1, 0, 0, if the next bit is 0 here, okay, in the sequence given, then we are going to the state A. We are going to the state A. And then at state C, we are checking for the input bit 1. If it is 1, we are going to the state D. And then from the D state, we can go back to the state C, because our sequence is 1, 0, 1, 1, 0. Okay, the sequence, the input sequence can overlap. The bits can overlap. In order to check the sequence again, we are going to the state C. And what is the sequence here? 1, 0. Again, if you are getting 1, again you are coming back to D, and then check for the next bit, whether it is 1 or 0. Again, if you are in state D, then the input bit is 1. Still, we have not detected the sequence total. We are in the state 1, 0, 1, 1. So the output is 0. Okay. Now, it transits to the state E. During the current state E, when the input is 0, again we are transiting from state E to state C. Okay, here again this you can start over from 1 0. Okay, so we are transiting from E to C. Again, if you are checking for the bits 1 0, again you will get 1 0 1 1 0. Okay, in this way we have to construct a state diagram, and after getting the sequence we are asserting the value output as 1. Okay, 1 0 1 1 0. Okay. Again we are going to the state C because we are having the transition from C to D with a 1 and from D to C with 0. So we can get another sequence and we can detect the sequence 1 0 1 1 0. So we are going from E to C here. If you are not getting the sequence output as 0 here, we are going back to B. Okay, because again B will be the initial state here. Okay, B will be the initial state. So we are going back to this state B, where it is starting from the state 1 0 1 1 0. Okay, in this way we have to construct the state diagram. Okay, first step is we have to write the states. Okay, we have to write the state from the initial bit. Okay, and then first we have to consider the first state, initial state, or starting state, or reset state, and after that we have to check for the sequences. Okay, the first bit, the sequence that we are considering in this example is, that is 1 0 1 1 0, 1 0 1 1 0, 1 1 0 1 1 0, 1 0 1 1 0, 1 1 0 1 1 0. Okay, here if you check this sequence input string, okay, here first bit is 1 and the next bit is 0 1 1 0. Here we got the sequence 1 0 1 1 0, so we are asserting 1 here. Next, okay, here they have mentioned that the required the detection of the required bit pattern can occur in a longer data string, and the correct pattern can overlap with another pattern. Here this 1 0, we are getting again 1 0 1 1 0. Here 1 0 is overlapped with another pattern, that is 1 0 1 1 0. So we got the sequence 1 0 1 1 0. So we got z is equal to 1, which means that the sequence has been detected. Again we are having 1 0 1 1 0. Here we are asserting 1. Okay, in this way we have to check for the overlapping pattern also, and then we have to check the sequence to assert the output variable. Okay, first state is initial state or reset state A. Okay, from here we are transiting to the state B. When we are transiting to the state B, whenever we are getting the initial bit 1, which is in the sequence 1 0 1 1 0, what is that? Z here is 0. Next, we are going to the next state. Okay, when we are getting 0, first bit as 0 will be in the same state A. Okay, if you are getting the first bit, which is correct bit, we are going to the next state. Now we are in the B, state B. Again, we are checking for the next bit 0. Okay, here 1 0 1 1 0. Now, whenever we are getting the next bit, next correct bit as 0, okay, our output is 0. Still we are not getting the whole 5 bits, so z is equal to 0. Whenever we are getting the input next bit as 1, we are not going to the next state. We will be in the same state, that is B is B. Then what is the input 1 and the output is 0. Now this B state will be the initial state. Okay, we can consider this as the starting sequence 1 0. Now we are going to state C if we get the two correct bits 1 0. Okay. Now if you are in state C, okay, when you are getting the next bit as 0 1 0 0, okay, all three bits are incorrect. Okay, this bit is incorrect. So again we are going to the state A. Okay, reset state. Okay, when the input is 0 and output is 0. Now when it is in state C, we are transiting from state C to D when you are getting the correct bit 1 1 0 1 and the output is 0. Okay, we are going from D state to C again because it is starting from state C. Okay, we are having the input as 1, so we are transiting again to C, and we are having input 0 and the output is 0. Okay, here we are getting the sequence 1 0. Okay, where the overlapping occurs, we can consider that sequence. When it is in state D, when the input is, we are getting three correct bits 1 0 1. Again, if you are getting 1, we are going to state E, otherwise we are going to state C. Okay, now we are in state E. If you are getting a correct sequence, that is 1 0 1 1 0, again we are going to state C, because we are having the starting sequence that is 1 0 from the state C. So in order to have the sequence detected, we are going back to the state C. If you are having the sequence, if you are having the bit 0, then we are asserting Z as high, which means that we got the sequence that is 1 0 1 1 0. Again, we are getting another sequence. It starts from this 1 0 1 0 1 1 0. Okay, 1 0 1 1 0. Okay, now if you are having the next bit as 1 instead of 0, then we are going back to the state B. If it is high, output is 0. Again, we are going back to the state B. We are starting from the next sequence. Okay, just we are going for the next bits. Okay, if you are not getting this pattern, or if you are not detecting the sequence 1 0 1 1 0, and if you are not getting that sequence, we are going back to the initial state, that is B. Okay, now that is 1 0 1 1 0 is detected. If your next bit is 1, then it is going back to B. Again, it checks for the next bit. Okay, when it gets the proper sequence, that is 1 0 1 1 0, it will assert this output Z. In this way, we have to draw the state diagrams. Okay, here we have to do the several attempts in order to get a proper state diagram. If they give the verbal statement or problem statement, we have to do or make several attempts to get the proper state diagram. The fifth correct input bit in the serial string is checked by the transition from state E to either state B or state C. If x is equal to 0, the fifth correct input, the system outputs a 1 and changes to state C. Why it is changing from state E to state C? It is that the strings can overlap, and first a 1 and then a 0 of a new correct string has been detected. If x is equal to 1, the machine changes from state E to state B, indicating that the first one of a new string has been detected. Okay, if your x is equal to 1, then again we are checking for the new string. Again, we are checking for the first one of a new string because our string that we have to detect is 10110. Okay, so we are going back to the state B again because the initial bit for the state B is 1. So we are going to the state B. At the end of this module 4, students will be able to design the sequential circuits using SR flip-flop, JK flip-flop, D flip-flop, and T flip-flops, and the Mealy and Moore machines. Okay, they are able to write the Mealy and Moore state diagrams and construct a state diagrams and then analyze the sequential circuit and get a state diagram from the sequential circuit. Thank you for listening to this session.